Okay, we're going to keep working on this review here. So we'll start with number 5 in this video. And it says, note the language used here, the rate of change of sand on a beach. That denotes that we have a derivative, right? Rate of change of the amount of sand on a beach is given by R of t. All right, so what we said before is there is some function out there, I usually call it A of t, which represents the amount of sand, okay? And that's measured in, so R is measured in dozens of cubic feet per hour, so A is measured in dozens of cubic feet, which is a little weird, but if you get 10, then that means 10 dozens, so what, 120? Okay, T is measured in hours. What time will the sand be the greatest? So again, we have an amount function which we don't know right off the bat. However, we know R of t is the derivative of A. So I know that A prime, the derivative of the amount, is just R of t. Cool. So I'm asked to maximize the amount of sand on a closed interval. So we always do the same way. You write, hey, I need to know where the derivative is 0. We're going to find those times. Now we use a calculator for that. So on my calculator, I just put in the function already here to y1. I'm going to change my window to go from 0 to 6. Okay, we're going to count by ones. And my y min to max, I'm going to leave negative 1 to 1 because I just care about where does it hit 0. So then we're going to graph it. And what we see is the derivative, which is r, right, we're graphing, is positive, which means the amount of sand is increasing. Oh, and then right after 3, it becomes negative, which means we're losing sand. Okay, and because we got that sine curve going, it's going to stay negative all the way until 2 pi, which is a little bit past 6, so we're not going to see that come back up. Okay, but when you zoom out, you would see it looks like a sine curve that's getting bigger because the function we're doing is e to a power, which is going to get bigger as t gets bigger, and sine of t is going to wave back and forth. So that's what that derivative really looks like if we were to zoom out on it. But we're going to do that. We just need to know where it's 0, and you can see there's only one 0, so second trace. We want that 0. It's around 3, so we'll say look between 3, enter, and 4, enter, and it looks like it's like 3.1-ish. And we get 3.14, oh, it's pi. Of course it's pi, because it's sine in there. It's 0 pi. And notice here too, this is a little weird thing. It says y equals 4.81 e to the negative 13. That's 0. That's just the calculator having some rounding error. That's 0.00481. That's 0 for us. So, like I'd always do here, I'm going to second quit out of here, and I'm going to store that number as, I'm not going to use A because I already used A for my amount function. I'm going to store it as alpha B. Cool. Boom. Oh, but it's just pi, which we know. Cool. So you can write pi here, or you could write, if you don't recognize that that's pi, you could write 3.14159. Cool. But either way, you want to call it A, or, well, I called it B on my calculator. B, or you can just write pi and use pi, because that's what it really is. But either way, no. Typically, we're given like some amount of how much sand there is, so we can find an amount function. But I don't know how much sand there is on the beach at any given time here. But we can still explain why we know that the maximum is going to be a pi, or B. Because the derivative on this interval, if the graph, is positive until pi, and then negative after. So my amount function must increase until pi and then decrease. So it only goes up and then down. So we don't need like a sign chart for this. The sign chart is good to use for us, but it's not for the AP test. It's not considered an answer. All right. So you're going to write in my sloppy handwriting the max amount of sand is at. Yes, so again, it says what time will there be a maximum, not what is the maximum. So as at time equals B, which is pi. So again, you can put B or pi there, it doesn't matter. And it doesn't say to explain, but the AP test is going to say to explain. So you'd say something like this is because, now again, if we had actual values, we would just find the values at the endpoints. And when we explain why, there's going to be one that's the biggest. But if we don't have that, we can't find the values. We have to explain why we know it's a max. So this is because R of t, which is a prime of t, and I'm allowed to say a prime of t because I defined A of t up here. All right? So R of t equals a prime of t is greater than 0 on the interval 0 to b and less than 0 on b to 6. Okay, you don't need to explain any further. Like, everybody understands derivatives, knows what that means, but if you felt like it, you could write this means. That says means. My handwriting is bad naturally, but writing on the computer screen doesn't help. This means the amount of sand, or we could say A of t here too, the amount of sand increases until B hours. Which we should put hours on our units up here too. B hours. It's snowing. You boys are excited. I see it. Awesome. Go play. It's snowing, folks. All right. It's summer of 2020 right now, and it's snowing in Columbia. Hey, guys, shut the door. They left the door open. Okay. So that's it. All makes sense. Very good. I got a lot of hopes. So look at number 6. It says you're taking a trip in your fabulous car. Excellent. During the trip, your air conditioner goes on the fritz and it only runs for the memory. The temperature is going to be like this, so that's the derivative of your temperature. Okay? Which means that tells you how fast the temperature is changing. And we know what's the average rate of change of the temperature, okay, for part A. But also, I'm skipping around here. Hey, at 2, we have 75 degrees. So right off the bat, though, because R is the derivative, I can say this. I'm going to call T, capital T of T, going to be temperature, okay? So I might write that somewhere. Capital T of T equals the temperature in the car. Cool. All right. So T prime of T is that, and because we know a derivative and a point, I know a formula for this is 75 plus the integral from 2 to t of r, which is the derivative, and you got to use a different variable here, x dx. That's an equation for the temperature. Cool. And then what's the average rate of change of temperature? So we could either do t of 14 minus t of 0, right, over 14 minus 0. That's going to work for us, and then we can use this formula here to find that. Okay, t of 14 and t of 0, all right, because we don't know either of those. Or you can remember that the average rate of change of temperature is also just the average value of the derivative. So that would be this. These are the same thing, because the integral value of t from 0 to 14 gives you t of 14 minus t of 0. Cool. So that's what I'm going to do there. And remember, since the average rate of change of temperature, it's going to be in degrees, Fahrenheit? Yeah, degrees Fahrenheit per hour. Okay, but we got to put this into our calculator here. So let's go to y equals. Here we go. Play along at home. We need r of t is what? Second square root of x. Okay, that's not what I want. Second square root of x. That'll do. Sine of pi x over 5. There we go. So I'm just going to drop that in there. So that's my r of t. Now I know that. And I need 1 divided by 14. That's the part up front. Math 9. We need to integrate from 0 to 14. The function. So I could have just typed it in there too, but I like putting a y1 so I can just grab it whenever I need it. Dx. Cool. And that's going to give me something. 0.449. So 0.449. And that's again in degrees per hour. Because the temperature, if you look at this, temperature is measured in degrees, and this is measured in hours. So degrees per hour. Cool. Same thing's happening here. This integral of r of t dt is measured in degrees. R is measured in degrees per hour, but the dt in the integral gives us measured in hours. Cool. But then the 1 over 14, so it's basically this. It's 1 over hours, that's this part, multiplied by the integral of r of t, which is degrees per hour. And then you're multiplying by dt at the end, which is in hours. So all those units cancel there, and you get degrees per hour. And it's degrees Fahrenheit, right? It would never be 75 degrees Celsius in your car. That'd be crazy. All right, and then B says, what's the maximum temperature from 0 to 14? So I see I'm asking these questions over and over and over again on this thing, because I want you to really understand this. We need to know where the max is. We got to find the derivative, which is R of t. And somewhere on this paper, for AP-wise, if you don't say that the derivative of our function is R of t, like usually you lose a point. You got to say that. So we need R of t equals 0. So you got to say that as well to get a point. Like they grade that. So we're solving that equation. And anytime you use a calculator to solve an equation or evaluate an integral or derivative, write on your paper like what you did, not like what you did in the calculator, but what you're solving or what you're integrating. So as long as you have R of t equals 0 and you solve it on your calculator, you're totally fine. So we're going to go from 0 to 14. So I don't know if you guys can hear my dog snoring, but she is feeling good today by the fire. So 0 to 14, we're going to graph R of t. This is just a sine curve too, similar to the last question. So you're going to see it go up and come back down. But it's not going to do it until 5 because it put that pi over 5 in the sign there. It's going to do it again at 10. It's going to come back up at 10. And it should go back down again at 15. But that's not happening because we don't get to 15. Okay, so you can find those zeros if you want to tell me they are 5 and they are 10. So that's the answer to this question. T equals 5 and t equals 10 hours. Cool. Now, it's not the answer to the whole question. That's the answer to where the derivative is 0. Okay. I have a math meeting in 4 minutes. So to find the max, I need to find the temperature at 0. So remember in the last one, I had to explain that the derivative was positive and negative, which explains that the amount was going up and then down. In this case, we could do that if we want, but we also can just find the temperature at all the critical values and the endpoints, and that's a whole lot easier to do than instead of explaining why. Okay, so if you have an opportunity just to find the values, just find the values. So we're going to find at the endpoints, and then we're going to find at 5, and then we're going to find at 10. Okay, now but looking at our graph here, we can see, again, this is the graph of the derivative. It's going to have to be at 5, which is a maximum, right? The derivative is going positive, negative. It's not going to be at 10. That's going to be a minimum. The derivative is going negative to positive. Or it could be at 14 because the derivative is positive leading up to that, so the temperature should be increasing. Cool. But to find them, we are just going to do what we've been doing with this. So it's 75, right? We wrote our formula for temperature plus math 9. And that's the integral from 2 to 0. It's okay to integrate from a greater number to a lower number on the calculator. That's fine. Remember, I told you, if you're doing area, you want to change that and switch the sign of the integral because you're always going to find area left to right. But we got to put in the function we're integrating, which is the function I put in y1, and then dx. There we go. And that should be less than 75 because this temperature was increasing. So 73.775. Okay. And then we got to find t of 14, which we're going to do the same thing. I'm going to hit second enter to get my whole thing back here. And just go back and change that 0, to a 14. And that finds a temperature of 14. It's taking 75 and adding the change from 2 to 14. So the change must have been 5.063 because the temperature in the car at 14 is 80.063. 80.063. All right. And the units always are all in degrees. Now, same thing. I'm going to go back and change that 10 to a 5. Or that 14 to a 5. 78.665. And then at 10, we're expecting that to be a minimum, but if you don't find it, you got to explain why you didn't find it. So this makes sense just to find it. To find the max, just check all the critical values. And this is going to be a min, 69.971. Cool. So the maximum has to come from one of those values because it can only happen at a critical value or an endpoint, and it happens at 14. So it says, what's the max temperature? Oh, by the way, see how this says justify your answer? What we're doing right now is our justification. We're showing I need to know where the derivative is 0, step 1. I'm finding all the possible maximums by checking the critical values and the endpoints, step 2. And then I'm going to write a sentence that just answers the question. So the max temperature is 80.063 degrees, right, Fahrenheit, technically. And we're going to say when. Even though it doesn't ask when, always put it just in case, because sometimes it says when, and students forget to write that. At t equals 14 hours. Just get used to answering both of them, when and what. Okay. That's it. What time is it? 11:30. I'm late for my meeting. What do we got left? 8, 7, 8, and then I skipped 9, and then just 10. Okay. I'll come back and do this later on.